and the full offset from your program machine. It tells the machine what direction you want to go if we do arc switches. Or it's some combination of this G01 straight line move, G02 3 arc move, and G00 rapid move that have been programmed all together in something we call a scan cycle, or sometimes even a macro. So remember, no matter how complex the motion is machine speed, it's either moving point to point in a straight line at its limit speed, it's moving point to point in an arc mode.
And he belabors this topic, doesn't he?
Or
in the video. He probably thinks it's important.
We're expecting the tool to be in contact with the working material. Basically, we're going to be making skips. When we do a G00 command, we almost always expect that we are not in contact with the working material. Just to move as quickly as possible from the beginning of one cut to the beginning of the next cut, from the end of one cut to the beginning of the next cut, or from the tool change location to the beginning of the cut, or from the end of the cut back to the tool change location. That's all there is to it.
So I guess the last class didn't end quite on schedule, and so we got in here a little bit late. This series of videos was supposed to start before the hour started, so that it would be done at about 3 minutes after the hour. So we've still got about 2 minutes here. I did say that we were going to have cool YouTube videos to get you guys in the mood. YouTube of me lecturing to the piece of paper probably wasn't getting you in the mood, so I had to liven it up a little bit here. Was anybody there at the, there was a live event here watching the thing? Anybody there? You were there? A couple people were there. So it turns out that at the beginning of that first video, you saw the part that was getting made there. If I go back here, so this part that's getting made right there. Do you see it on the robot? It's very possible that the one that video is in fact the one that's on this right side of the robot right now. So WPI is one of the sponsors for ByteForce. My company is also a sponsor for ByteForce. They needed some of those parts made the week before the competition. Paul, who's the team owner there, he reached out and said, "Hey, can you guys make those at your company?" And I said, "Well, no, we're busy in production right now, but we can make them at WPI." And so since WPI is also a sponsor, that was pretty cool. So the VM2, the same machine that you guys made the second operation on your Y block, that's where those pieces were machined. And in fact, after the competition started, so they get down there, so they shoot all that over like a 2-week period or something like that. So they stretch it out over several months when they broadcast it, but they shoot it over like a 2-week period. And so they got there on Saturday to start on Sunday. On Monday, he said, "I need some more of those." And by Tuesday, he had some. So thank you, overnight shipping. Cool thing. Fun little side story. Get us excited about today. What are we talking about today? Did anybody, what do you got? You're pointing to him because you knew he knew the answer? Cool. We're talking about CNC machining. Yeah, what specifically about CNC machining do we want to talk about today? And I'm going to try to stay on schedule. What specifically are we going to talk about CNC machining today? Yeah. All right, so flow and operation. So we introduced this topic yesterday, right? At the end of class. We got to, and I even made a note to myself, start on slide 12. Check it out. Yeah, 12 wasn't the right number, though. 13. It was pretty close. Start on slide. So I think this slide was up on the screen when we ended lecture yesterday, right? just quick recap. All right, so in order to make any part, first thing we have to do is decide what manufacturing process or processes we're going to use to make the part, right? And we decided that sometimes 3D printing is a good choice, but sometimes it's not, especially when you have a lot of parts to make. They're getting better at the 3D printing thing. Pretty soon they'll be there. But I'm going to guess for most of the rest of my lifetime at least, and for probably most of your lifetimes too, CNC machining will still be a major factor in our economy. It will still be it's hard to say most significant process, right? Because we talked about manufacturing businesses, it's actually sales that's the most significant process, right? If there ain't no sales, there ain't no company. Nobody's going to be doing this manufacturing. But the CNC machining is the way that we make stuff today, primarily around the world. So it's important. It's good for us to understand it. If we've decided, and so this diagram kind of presupposes that we've decided to do CNC machining, right? Because we talk about things like tool paths, right? And so we've gone that direction. So when we've decided to do CNC machining, what is it that first thing we do is figure out what process or processes that we're going to use to make this part, right? And so our Y block, which was the example part that we were looking at, we could do it in 2 operations in a CNC mill, or 3 operations in a CNC mill, depending on how you wanted to do the fixturing, right? So in order to decide that, we really needed to understand how those operations work, right? So so just describe very quickly, Trevor, how a 2 or 3 axis milling operation works. What is the process that it does? Okay, yeah, so quicker than that, what has to happen in order to remove the material? The tool has to be spinning, right? And the tool has to move in some programmed tool path, right? Through the material, and it's like the thing the art student asked the instructor, how do I carve an elephant out of this block of granite? And the instructor says, chip away everything that's not elephant, right? And so that's how our CNC machining works here, is we're really chipping away everything that's not the part that we want. Okay, so Mike, our CNC machine tool, if we've got our part fixtured in a, here's a part. We've got, or sorry, do we fixture the part or the workpiece? We fixture the workpiece, right? We've got our workpiece fixtured in the CNC machine tool. Assuming that I'm standing and I am aligned with the Z-axis here, what kind of features can I make on this part? If I've fixtured it like this in a vise. So I've got my part fixtured in a vise. Let's quickly just draw what I'm talking about here. Right, so if we're in the CNC machine, I've got my, so I got my vise, the end of my vise is here. The vise jaw sticks up just a little bit above that. I've got my workpiece. And so some of that workpiece is inside the vise jaws, right? So I'm drawing hidden lines because you can't see them. Some of it's sticking up above the workpiece. Now there's another vise jaw in the back. So this is like the front view, like you're looking in through the door of the machine. The side view then would be vise jaw. We put these things called parallels in there. We put the workpiece on the parallels, right? So I'm looking from the side now, and so then the vise body is down here somewhere, right? So what kind of features can I make on my part with a CNC milling operation now, once I've fixtured it in the machine? Go ahead. So I could drill holes into it in this orientation, right? So I could make holes that went down that way. Could I make holes that go in this side? No. Well, I could, but I have to take the piece out and flip it on its side, right? Okay, so I can make features that I can see from the top down. That makes sense? So I could go around the outside, right? We call that a contouring operation. If I go around the outside, I could make, so if we look at the top-down view here, get my parallels in there holding the part up. Vise goes out like that. So we're making top-down view. I could make a feature that goes through the part right there, right? What do we call that feature? Does it have to go through the part to be called a pocket? No. It could be a blind pocket, doesn't go through the part. A through pocket goes through the part. We could make holes. We could make threaded holes or tapped holes, right? We could cut threads into those so you could put a bolt into it. We could go around the outside to make it some other shape than rectangular, or we could make it shorter, right? We could remove material from the top to make it shorter. So if we're removing material from the top, we call that a facing operation. The top of the part is the face in a milling machine. That's the top face of the part. In a lathe, the end of the part is the face. So in a mill, the top is the face. In a lathe, the end is the face. What's common about the top in the mill and the end in the lathe? Yeah. That's true, but that's not what I want you to answer, Tim. Sometimes. They don't have to be flat. Yeah? No, it has nothing to do with distance, yeah. Well, we can do stuff on the face. We can do stuff on the edges. In the lathe, when we're doing stuff on the edges, we call that OD, or outside diameter machining. In the mill, when we do stuff on the edges, we call that contouring, or side milling. Yeah? It's the most accessible. So in fact, the z-axis is lined up with the tool orientation in the mill. And the tool spins, which means that face is nominally perpendicular to the z-axis. In the lathe, the z-axis is lined up with the spindle, because the z-axis is always lined up with the spindle. And so in the lathe, the plane that makes that end of the part is perpendicular to the z-axis. So the face is perpendicular to the z-axis. And all right, so we can do those things. Once we've decided to do a particular CNC operation, once we've decided to do that, then what do we have to know in order to do the rest of it? That's what I want to talk about next. So once we've decided to do a particular CNC operation, whether it's a pocketing operation, a facing operation, a drilling operation, some kind of hole making operation, once we've decided that, see if I can switch over here. Sources. Hey, it worked. And it's not upside down or anything. On the other one, I'll get the agenda back up since this cool classroom lets us do that. Somebody try to keep me a little bit on track. How are we for time right now? It is 17. At 17, yeah, we're behind. Okay. But this says, oh, it says 13. Oh, but it's 117. The date's 17. 13. We're right. We're totally right on track. Sweet. Sort of. We're doing the 06 stuff. Okay. I had to talk faster. What are we going to do once we decided the operation? Yep. We gotta know what tool we're going to use. Before we can, so actually, let's step back just a second. Before we can decide the operation, we actually have to know what the part looks like, right? We have the part. We got to know what the finished part geometry is, or geometry. And surface roughness, all that stuff. We got to know that. We actually have to know what's the geometry and material properties of the stock material also. So before we can even select the operation, we got to know what the stock material is. So All right. Once we know this and we know this, we can start getting into tools, and we've chosen our operation. I was supposed to write all that stuff down before I asked you that question. Part geometry, workpiece, stock, operation. Actually, I think at this moment, we also need to understand our fixturing. Now, I know people don't always do it in this order, but if you haven't figured out what it is you want to make, then you got no business picking out tools for it, right? You should concentrate on figuring out what it is you want to make. It's very difficult to ensure that you chose the right tool if you don't know anything about the workpiece. And so the tool we can pick before we pick the fixturing, but once we get to the point where we have to decide the tool path, one of the critical things that we have to do is make sure that the tool path does not have the tool run into the fixturing. So I think we have to have that fixturing defined here. So we got to know all this stuff. Now with our Y block, we said we could cut it in 3 operations, right? If we cut it in 3 operations, we have to do this 3 times, right? Before we get to this and this. Okay, so we get the tool figured out. Once we have the tool, since we already know the workpiece, what else do we know? After we've chosen the tool and we know the workpiece, we also know, well, with the workpiece material, so we know everything about the tool because we have the part number from the tool manufacturer. Because we've chosen the tool now. What else do we know automatically once we've chosen the tool? Yeah. We don't know the offset until we put it in the machine. But we do know what's the correct feed speed depth of cut, right? We know the process variables because they're determined by the tool. So we know feed, speed, depth of cut. And we know that because the tool manufacturer provides us with that information. We've looked it up on some other chart, or we've experimented with this tool and we know what feed, speed, depth of cut to use for that tool. All right, so once we've got the tool, process variables, feed, speed, depth of cut, what's the next thing we're going to do? Yep. We've got to create the tool path. And so it's entirely possible for us to sit down there, and if we know that G01 makes the tool go in a straight line, and if we know that G02 makes it go in a clockwise arc, and G03 makes it go in a counterclockwise arc, and that G00 makes it move as fast as it can to the spot we told it to go to, then we could sit there with a piece of paper, and we've got a drawing for our part, right? We've got the art. We know the shape of the part. We could sit there with our piece of paper, and we could say G01, X1, Y2, Z14. And then we could write the next line of code, and we could write the next line of code. And based on the information that you have right now, if I gave you maybe 4 more G codes, you could write the code for a G and M codes, NC code things. You could take a drawing and write code. You guys could figure it out. I have no doubt that you could, because it's simple geometry. And the only 3 things that the CNC machine tool does is move in a straight line, move in an arc, or go rapid. All the other, there's probably another 170 commands that are possible. But all those things do is turn something on, turn something off. Turn on the spindle, turn off the spindle. MO3, MO4. Turn on the coolant, turn off the coolant. MO9, or MO8, MO9. Right? So all the rest of it is just helping it get ready to do those motions. You guys could write that code if you simply had a reference sheet. Well, maybe this should be the homework. Oh, think about it. Okay, to do that. As we get into creating the toolpath, though, there are things that we must consider. So one of the things that we must consider is how is the tool going to enter the workpiece? So tool spinning, happy up here in space. Tool moved to workpiece. That instance, so our feed speed, depth of cut, the stuff that we look up from the manufacturer, they're expecting that that's a steady state thing. They're expecting that it needs that feed speed, depth of cut when it's in steady state, when it's just moving along. When it enters and exits, different forces, and it's like the difference between statics and dynamics, right? So if we have a steady state operation, we can have velocity, but as long as it's constant velocity, it's statics. It's a statics problem, right? You guys have all had statics and dynamics, or most of you have, right? Yeah. So as long as it's constant velocity, there's no acceleration, it's statics, not dynamics, right? It becomes dynamics once there's acceleration. There was supposed to be another piece of chalk for me to pick up. Found it. Okay, so we got to think about how the tool is going to come into the part, how it's going to come out of the part. What's the surface speed? So if we look at the bottom of an end mill, it looks something like this. Maybe we'll draw a 3-flute end mill. And so we look at the bottom. If you looked at the side view, there'd be a spiral going up the side, right? We're looking straight down at the bottom of it here. It's not enough to just press the document camera button. You have to press where you want it to go also. If we're looking at this, what's the surface speed here? Yep. RPM times diameter times pi divided by 12. If the units work out, that's what it is. Did you guys know that engineering's math? Just a bunch of word problems. Cancel the units. RPM, all right, so surface speed here. What's the diameter? What's the diameter here? It's D, right? It's the diameter of the tool. What's the diameter here? What's the diameter at the center of the tool? 0. If I want to have a constant surface speed, what's the RPM need to be? Infinite. We do not own any machine tools with infinite on the spindle settings. So the surface speed here, no matter what, will be 0. Which means these tools do not really like to plunge down into the workpiece material. You believe that? In fact, can it cut? All of the cutting comes from the surface speed. We said that a couple lectures ago, I think. All of the chip formation, all that cutting happens because of the surface speed. Now, the feed rate and the depth of cut puts the tool in the position where it's able to cut. But the cutting happens from the surface speed, which means there ain't no cutting happening at the center of the tool when it plunges down. But it goes into the workpiece. I've seen it happen many times. Plunge that tool down in there. It goes into the, you guys saw it happen, right? Did you? Did we do any operations where we plunged in? No. Oh, the drilling operation plunged in. Yeah, they actually designed the tip. They call it the chisel tip on the drill, especially because they know they're plunging in at that point. And so the surface speed from that plunge for the drill with the tip that's made the way it is, all of it comes from the feed rate, right? Because there is a component of that cutting that comes from the feed rate. But basically what happens at the center of the tool, and until we get about, I don't know, maybe, I wonder if anybody's ever studied this. How far out from the center do you have to be before there's really cutting happening? When you're inside that zone, it's just pushing the material around, which means the force of the motor is pushing the aluminum out of the way. So, so we don't like to plunge directly into it. So if I don't want to plunge and I got to make a pocket in the center of the part, what could I do? I forget your name. Would you ever? No, I was actually thinking of the really cool sweater in front of you. It's a pretty cool sweater. You can come in at an angle. What's your name again? Molly. So Molly wants to come in at an angle. We call that ramping. So if you got the XY moving sort of in a straight line and the Z moving in a straight line, that's a ramp into the part. If you do that, then you never actually have the center of the tool in contact with the workpiece. Now, what if you didn't have a long distance to go over for your ramp? Yes. You could do a helix. So we could ramp down a circle, right? And so, so we have to consider how are we going to enter the part. You go back here. Nope, this one. Oh, and amazing. It was, in fact, the next slide. Sometimes you think you know what's going to happen. All right, so first thing, and you guys have seen some of this already in Esprit, right? So first thing you got to do is you got to tell it what tool you're going to use. So here we told it we're going to use a 3/8 inch end mill. There's other stuff on this page. Everything else that's in this tab, that is a process variable, but we're talking about the most important process variables today. We got to put in our feed speed depth of cut. And so for our feed, we put in this 0.0035. Can you guys see that? It's hard for me to see from up close. No, it sucks. But believe me, that's what it says. It says 0035 there. And so there's two boxes next to that X, Y, and the Z feed rate there, right? Why? You guys have all seen this in Esprit, right? You've had to type this in at least once. Why is there two boxes? What's the relationship between them?
I think one of them has to do like per fluid.
So it's units, and so so it's the per flute units or the per minute units. If you type one of them in, it calculates the other one for you. Isn't that cool? So when you're doing a quiz and you're wondering if you did the calculation correctly, you could just open up Esprit and check. As long as your tool is defined correctly, right? Okay, so that's there. Now here I've got the X, Y, and the Z feed rate exactly the same. Is that what you learned in lab? That X, Y, and Z feed rate should be exactly the same for a tool like this? What did you learn in lab, Stephen?
I think XY figure is 0.003 and this is 1.006.
Yeah, so is that like a quarter? 0.0006 to 0.003? A fifth, a quarter, a tenth. It's smaller because the tool is not intended to feed in the Z direction. Sometimes you actually have to plunge that tool in. When you do actually have to plunge that tool in, you have to go slower. Now in this particular program, I didn't care. I left them both the same because I was never intending to let the tool be in contact with the workpiece material when it was moving in the Z direction. So I already knew that my tool path wasn't going to allow that. I left them in there the same, so when it was moving in Z direction and it was not in contact with the workpiece, it didn't move really slow. I did that. So feed, speed is up at the top, right? So speed's up here. We got cut speed, RPM or SFM. They think here instead of F, they say SPM, surface per minute. I don't know. Some software guy wrote the interface. Probably wasn't a machinist. But 6,000. Why 6,000 here? Oops, back. Why is that 6,000 up there? Somebody else. Somebody guess. Why is that 6,000? Michelle. See, you're in trouble because I remember your name. You don't need the card. That is as fast as the spindle in a mini mill will spin. Now, if you look up anybody know what the recommended surface speed for this end mill is in aluminum? It's up to 6,000 surface feet per minute. With a 3/8 inch end mill, how fast would the spindle have to spin to get to 6,000 surface feet per minute? I don't remember, but it's something like 60,000 RPM. We don't have any spindles that go 60,000 RPM that can hold a 3/8 inch end mill. So what we do is we go as fast as we can go. And then if we're programming as the per tooth or the per flute feed rate, then it will slow down the feed rate to compensate for the fact that our spindle's not going that fast. Okay, so feed speed depth of cut, that's all in there in the Esprit. It talks about axial depth, radial depth, yeah. The feature, yeah, entry and exit. Okay, so here's where you get to put in, is it gonna ramp in? Is it gonna, so here we chose ramp along pass. There's always a thing down here, if entry fails, there's two options, skip and plunge. Always have it set on skip. If you get an error message when you create the operation, when you click OK, and it says that something's impossible, to test if it's the entry move, switch it to plunge and see if it compiles the code. And if it does, then you know there's something wrong with your parameters for the entry mode. Flip it back to skip and figure out what's wrong with your parameters. That's just a little troubleshooting thing when you're doing the code. Entry, exit, clearance is the last thing we want to talk about here. Clearance. So when you are in the program and say it's got a pocket that it makes over here, and then a pocket that it makes over here, the tool needs to come up above the workpiece, go over, and then enter the next pocket. And so you set a clearance plane to say how far up should we go when we're moving between those operations with the same tool. And it's especially important if, for example, when you're fixturing your workpiece, so here's my workpiece, top-down view, things like that, and I got a pocket over here and a pocket over here. Well, I could fixture the workpiece to the machine tool table, right? What's the fixturing have to do? Has to keep the workpiece from moving when I'm cutting it, right? That's the function of the fixturing here. I could fixture it down by putting a strap across it here that extends beyond it on both sides with a bolt that goes down like that. If I have done that, and that's a very common way to fixture these things, when I move from pocket A to pocket B, I need to make sure that my clearance plane is above the thickness of my strap, right? Otherwise, what happens? Tool breaks in half every time. Unless, it's entirely possible that the tool just cuts through that strap like it was butter. Depends on what materials you're cutting, what feeds and speeds you have programmed, and what rapid setting you have selected in the machine when it rapids the tool into it. Because I have totally seen the rapid move just cut the fixturing out of the way and not damage the tool at all. But we call that a crash. You guys know what you have to do when a crash happens and you're operating a machine at WPI? What do you do if the machine crashes at WPI? What's that? E-stop if you can on time. E-stop frustratedly if you can't after it's over. I mean, you can't help yourself usually. I actually have a repetitive stress injury in this shoulder. And it was one of those things that shows up at a annual physical, and the doctor's like, anything else bothering you? And I'm like, well, this shoulder's always sore. And he moves all around and feels it and pokes it, and he's like, oh, it's like a repetitive stress injury. It's sort of like tennis elbow. You get it from making this motion, and since I was never a Nazi, I figured it wasn't from saluting. But I just started laughing when he said that. He says, you know, it could actually happen from one strenuous instance of it. And I said, no, I make that motion all day long, usually diving between the students at the machine tool to try to get to the emergency stop. And I just stopped doing it because it's cheaper to fix the machine than it will ever be to fix my shoulder. And I've just gotten used to feeling the vibration through my feet when the machine jumps a little bit and then lands again, because the lathe turret, that's the thing that holds the tools, runs into the chuck jaws on the spinning chuck. Who's heard it? Anybody? Anybody been in the room when it happens? It shakes the building. And I know for a fact that it's a $2,000 service call. Because what happens every time is one of the bolts, or 6 of the bolts that hold the turret in place, they shear. I've never seen the turret fall off, but it's always not in the right position anymore. And I just say, hey, that's a $2,000 service call. All right, so, but if that should happen to you, once you've gotten all the e-stop out of your system, and certainly if you think it's about to crash, hit the e-stop. If you hear something that doesn't sound right, go ahead, hit the e-stop. If it wasn't actually crashing, you can probably recover from that. Now, if you think at some point in the future it might crash, what should you do? You could, but if you think it's at some time in the future, you get some other options. Yeah, Mike. You can hit feed hold and look inside, and at that moment of feed hold, the code, the line of code that's operating at the moment of feed hold will be highlighted. And you can set it to what's a distance to go thing. So you can look at the line of code, you can look at the distance to go and say, hey, does this make sense? And if it doesn't, go ahead and hit the e-stop and figure out what's wrong with your setup. So beyond that, when all that is done and has happened, we should I was saying low battery, but it should still be going. Yeah, it's still live. Anybody got one of those lightning cable things? I can fix the low battery problem, you know, like the iPhone charger cable. Nobody's got one in their bag. I think I got a USB thing right here. Let's see if that fixes it. I thought about bringing one and I forgot. This is a second. Oh, even better. That is really short. That's not going to reach. The charger would make it fall down. No, I'm good. But she's prepared. I think I can plug it into this USB on the side of the monitor. Or is there? It asked me if I wanted to allow the computer to access the photos, so I guess it's plugged in. All right, sweet. Back on target. All right, crashing machine tool is WPI. What do you do once the crash has happened? Anybody know? Anybody? Anybody? Yes. You could do that. They're going to give you some instructions. I mean, you actually should do that. Tell one of the lab staff, especially if you don't know why the crash happened. Especially if you need help troubleshooting it. What else? What's next?
There's like a web page you have to go to.
Yeah, it's actually easier than a web page. Send an email to ibrokethis@wpi.edu. You are required, and there's signs up all over the shop that remind you of this. Send an email to ibrokethis@wpi.edu. You are required to tell us what was going on. What were you doing? What was the result? Please include pictures. So I'll see if I can find. No, it's on my phone. I'll post a funny picture of an I broke this that I had to send recently. So please include pictures to help describe what happened. You then have to estimate the cost of your mistake to WPI. So say you broke a tool. We want you to do a little research and find out how much that tool cost. Say you broke the Z-axis motor controller. I can let you know that that's about $6,000. And I don't know, that was probably not a student. All the expensive crashes that we've had at WPI have been staff members. And they have been staff members. I remember the very first week we had those CNC machines at WPI. So before the grand opening of the facility, right, first week, 2 of the machinists that worked there were both trying to learn how to do this because neither of them had ever used a CNC machine before in their life. So one of them got something all set up in the machine, then he went to lunch. The other one comes in and he's like, all right, how did that tool offset setting thing work again? And so he's fiddling around with setting tool offsets, and then he's like, oh crap, it's lunchtime. So he turns off the machine and goes to lunch. First guy comes back from lunch, thinks the thing that he's got all set up in the machine is still set up because he set it up, he went to lunch, he came back. Machine looked the same. Cycle start. Spindle nose into vise. Spinning. Gearbox spindle gone. $10,000 first week. I got a good friend. He was a machinist at a company where he worked. He actually started there sweeping the floor. Then they had him start loading parts in the machine tools. Then he started programming the machines. He went to some classes to learn to program. And so then he was like the guy. He was the guy that wrote all the programs. His boss says, we got to get those to the airport by 9 o'clock. What happened at 9 o'clock? What happens at 9 o'clock? Anybody know? Last cargo flight to California leaves. Got to get those parts to the airport by 9 o'clock because there's a guy in California that needs them tomorrow morning. Right? So he says, I'm going to reduce the clearance planes. Right? If I reduce the clearance planes, there'll be less rapid motion. The parts will get finished faster. Right? So he quickly goes in and edits the code. Reduce the clearance planes. He's like the man. He knows what he's doing. Except he confused a Z and a Y. So he typed Y where he meant to type Z, or he typed Z where he meant to type Y. Gets back in there halfway through the program, bang! Spindle nose into part. He walked out the door, got in his car, went home. Didn't say a word to anyone. Now, I've heard the story from the boss and from him. The boss said, it took me 3 weeks to get him to come back to work. I had to have him there. He was way more valuable than the $10,000 spindle, right? Because he was the guy that knew how to do this stuff. It was a simple mistake. Anyone could do it. Which is one of the reasons why we don't let you guys write G-code manually. It's one of the reasons that when you need to fix your program, even if it's a simple fix and you can just go edit the G-code, we tell you to pivot your feet, go back to the CAM software and fix in the CAM software. The other reason we do that is because you think you're only going to make this part once. But you're going to make it for your MQP, let's say. You're going to install it into the assembly where it goes. And then you're going to realize, I need to make this little change to make the thing work better. And then you're going to go back and you're going to make almost exactly the same part, or maybe even the same part, maybe just broke it. And if you edited the code manually on the controller, you're going to have to remember what all those edits were. And you're going to have to do it again. If you just fixed it in the CAM software, then it's just fixed. So that's the other reason we do that. I went just a little bit out of order. I went to operator checklist, but we also still want to talk a little bit about NC code. Oh, sorry. Local PC. Oh, hey, I did it right. Okay. So we've seen this stuff. All right, so you guys have seen NC code when you're at the machine? Right? You see it scroll past as you're going along. It turns out all the little codes mean something. If you're looking at it and you see N and then a bunch of numbers, I don't know if we always put so many zeros in there. We're anticipating a long program. That's a line number. What it does is it helps you if you have to restart a program in the middle. So say halfway through you had to change the tool because the tool wear out. You could stop that. If you remember the line number, you could actually restart the program on that line or a couple lines above that. We usually like to start at the tool change above the one, so that we make sure it's got all the right tools, it's got all the right offsets called. But so those line numbers are just for that. Comments in your program are going to be inside parentheses. When you're in a spree and there's a little comment thing at the bottom of the box, you can write a comment. Then it will show up in the NC code at the beginning of that operation. So here it says first tool change. Here it says start of operation solid mill pocketing. So the start of operation solid mill pocketing, you know each of those operations in a spree has a name thing. If you name them with something identifiable other than solid mill pocketing, because let me tell you, if there's 67 pockets on your part and they're all named solid mill pocketing, that name is not very useful. But you can find that operation again. And it's especially helpful if you're trying to debug something going on. There's G-codes. G-codes primarily have to do with motion of the machine. So we had our G01, G02, G03, G00, right? Those are straight line, arcs, and rapid. G53 is kind of a special one. It says on this line of code, ignore the work coordinate system that has been selected and use the machine's coordinate system. Somewhere here, there's our G54, right? G54 tells it, use the work coordinate system that's associated with G54 in the machine tool controller's memory. And so when you get, I think next week, the week after, you're going to be doing labs where you're setting tool offsets and work offsets. When you set those work offsets, there's memory registers where you put in the XYZ coordinate for the feature on the part. And so you say, here's the center of the part, and then your program is based on that. What that lets you do is it lets you run the same program in many different machines. You don't have to know the machine. You don't have to know where the fixture is when you write your program, stuff like that. So G and M codes. M codes tend to turn stuff on and off. So M09 turns the coolant off. M06 operates the tool changer. You could guess this line of code here, T8 M06. Anybody want to guess what that line of code does? Trevor, what do you think that line of code does? You're like right in the line of sight so I can call on you. I can see your name. It's okay to guess wrong. T8 M06. M06 operates the tool changer. What do you think the T8 means? Yeah. No. Yeah. Tool number 8, M06. Take tool number 8, put it in the spindle. That's what T8 M06 means. M03 starts the spindle clockwise. Stuff like that. There are lists, reference lists, where you can just look these things up. In fact, I think every machine tool we own at WPI has a sticker on it that tells you what all the G and M codes are that machine can operate. I know that every machine tool that we have at WPI has a compartment with the operator's manual that has a list that tells you what all those G and M codes work. And I know, Siri, what does G01 mean? Yes.
Use your iPhone to search the web for Siri. What does G01 mean?
All right, you can't use your damn watch, but you can use your iPhone. Start code, yeah, that's stuff at the beginning of the program. Oop, come on. Oh, you guys are starting to pack up. I heard like bags fidgeting around there. I thought I was out of time. I have 4 minutes left. So program name. In our thing, we do program name. We put it in here. Yep, your program name. If you're writing a program and you don't use a very descriptive name, in fact, if you use the default name that's in the template that we give you, and then you're not going to be able to identify your program on the machine as compared to somebody else's program on the machine. So use a program name that you can identify what it means. When we get out to the machine, you go to, if you guys have not loaded code on the machines yet, you'll do that later in the lab. But you get out the machine, you've got all these keys over here on the right-hand side of the controller that are different modes of operating. So there's a memory mode. You guys have done memory mode. Probably haven't done edit mode. And so there's list program mode. You go to list programs, it's going to show a list of program numbers and program names that are in memory, or there's a way to load them onto the machine. You guys will do that in lab. Again, you can put descriptive comments. It helps you if you're going to go back and use that same NC code again a year from now to remember what's going on. And that'll happen frequently in industry. So we can program in inch units and metric units. And but you got to tell the machine which one it is, and you got to change the mode in the machine so that it knows which kind of code to accept. It does tool changes. There's code for the tool changes. Put the comments in there. In the mini mills, you guys have operated mini mill, most of you? Half of you have, maybe? You'll notice when it does a tool change, the Z-axis goes all the way to the top. The table moves all the way to one side. The Z-axis comes down, it operates a tool change, goes up, Z-axis goes all the way to the top, the table comes back. We do that because there's not a lot of space between the table and the bottom of the tool in that tool carousel. And if you happen to have a piece of fixturing that's in the way, the tool rotating around in the tool carousel will hit that piece of fixturing, but it's still attached to the tool carousel. And it will break the tool carousel. So try to avoid that. There's one of those mounted on the wall in there. Yeah.
Does that, like, does Spree put that in by default? You choose the email?
If you choose the mini mill post processor, it goes in by default because in the code that defines the post processor, we hard coded that in. So we edited, and that's the thing. So all CAM software, Esprit, Fusion, the SolidWorks thing, whatever CAM software you're using, it has a tool that goes from what the CAM software understands and what the machine understands. That's called the post processor. In Esprit, we can freely edit that, and we can make those kind of changes, which is one of the reasons we use Esprit. Here's our length offsets. Talk about how to do it in the machine. Two motion. Operator checklist, right? Well, the last class went over. I can go over just a moment. Operator checklist. What are the 6 things on the operator checklist? What are the 6 things on the operator checklist? You've had to use it in class, right? I asked you to study it. That was one of the 3 pages I asked you to study. What are the 6 things on the operator checklist? 1, simulate in the CAM software. It lets you know what the computer thinks the program is going to do. When you simulate in the CAM software, you got to make sure that you have collision detection turned on, for example. Otherwise, you may not see that it crashed and you programmed it to crash. 2, you have to set the tool offsets. You have to tell the machine tool how long the tools are and sometimes what the diameter of the tools are. And we'll teach you how to do that in lab. 3, you have to set the work offset. You have to tell the machine tool where is the reference point on the workpiece. That's 3, right? Halfway done? 4. Anybody guess what 4 is? Yeah. Simulate on the controller. You must do the 2 work offset ones before you do the simulate on the controller. Otherwise, that simulation on the controller has no meaning. You should do the simulate in the CAM software before you do the simulation on the controller. If it doesn't look the same, if it looks like one thing in the CAM software and something else on the controller, you don't have the right program. That's 4. 5, reduce the rapid rate. Rapid, again, is when it's not intending to cut the workpiece material. Reduce the rapid rate to something that you're comfortable with. And 6, for each tool as it's approaching the workpiece, press feed hold. Look at the line of code. It will tell you how much further it's going to go. Look at the distance to go display and say, does that make sense? If it doesn't make sense, don't continue. We generated this checklist mostly based on what we learned from the I broke this emails. Since we have deployed the checklist, we have had 0 expensive crashes. And we have not had a single crash, with a minor exception, that could not be attributed to somebody skipping one of the steps on the checklist. There's one exception. We did have a bug in our post. It was, in fact, a known bug. And in certain circumstances, it would make the machine tool crash. And in fact, one of the staff crashed the machine tool that way last week, while he knew that 2 of us were at that moment fixing the post to make the bug go away. But at any rate, shit happens. And when it does, email ibrokethis@wpi.edu. And somebody needs their charger cable back. Whose is this?